Hello, can you
Uh,
hear me?
yes, sir. We can hear you. Okay. Good afternoon to all the speakers, panelists, and students. Welcome to the second day of the workshop today. And we have two interesting sessions. First, we have a keynote talk by Mr. Ravi Shankar Savita on quantum computing, its cycle, practical application, and future roadmap. Mr. Savita is the head of emerging technologies at Virtusa, based in New York City, USA. He has 17 plus years of experience in leading programs and working with senior managers on strategic and operating initiatives. He did his MBA from IIM Ahmedabad and executive education from MIT on AI. Today he is taking this session at 4:30 a.m. EST. So we are extremely grateful to him for doing this. So sir, I'll hand over the mic to you.
Hey, thanks. Good afternoon, good morning to everybody, and it's pleasure to be here. Um, just to check the logistic, I'm going to share my screen so that we get that out of the way. Can you guys see my screen? Good.
Yes, sir.
So what I'm going to do is I'm going to walk you through what I have been seeing in quantum computing of the late. Um, Virtusa as an organization is very digital engineering focus and digital transformation is one of the key driver. And as part of the emerging technology group, um, we started investing um, in quantum computing in way back in 2018. So one of the co-speaker who is going to be panelist is with me from 2018 in working on various dimension of quantum computing as it matures and as industry is looking to adopt it. So what I'm going to talk in next 15-20 minutes is how we have seen and what is the reality check apart from all the news coverage that quantum computing is having around industry adoption. First thing first is spookiness is exciting, and there are various. When we talk about quantum computing, there are kind of weird use cases that pops up, and there are lots of theoretical use cases that pops up. I have been talking about quantum computing application with at least 15-20 head of innovation in large companies. And the reality is slightly different. The reality from business perspective is very that small, narrow, um, real value addition use cases, or how do we really get this kind of thing as a very robust engineering uh, technology implemented in an organization or in any of the workplaces. So probably the way uh, that quantum computing is getting interpreted in real world is there's definitely there are lots of innovation, research, or R&D going on to go after getting quantum computing device itself a reality. But apart from the spookiness, where is the reality check from industry point of view? That is a very prevailing threat that is observed across the globe, so to speak. But behind that, there are lots of real research going on, and I have been fortunate to work with some of the leading research institute organization who are spending millions of dollars and lots of in engineering powerhouse in getting some of these things reality. There are very special uh, educational tours. There are lots of collaboration going on to get this device, so-called shiny device, for finding the eternal truth of the universe in reality. And as we probably know, that there are many uh, announcement, media coverage, um, uh, various news articles that are there, which is kind of leading towards that quantum as a computing device um, is getting to reality. Now, I think the real message that comes from all of this is not a point event in so to speak, that yeah, we suddenly one fine day we will have a quantum device with 1,000 qubit or 2,000 qubit right in front of us. I think the real progress that comes out of all this um, news and media coverage is there is substantial investment, there is substantial desire, and there is a substantial thrust focus towards getting this in reality. And as probably all of you might have gone through these articles or announcements, there is a very good um, coverage in Nature itself, Nature magazine. There are various dimensions of supremacy that we are talking about in terms of complexity of handling simulation or computation logic as compared to the classical computer and things like that. There are ways that how communication, quantum communication, probably the China announcement is towards that, that how quantum communication can itself render lots of result. Back in India, I know for sure there is a very large organization. I cannot quote its name because it's very confidential and I'm under NDA. But there is a very large organization who is investing quite a substantial amount of R&D funding towards quantum-based communication and what will be the shape of internet in the world of quantum communication. So yeah, the way that probably industry is evolving, this announcement is definitely the right steps towards getting quantum a reality, and that's how I think probably the industry is looking at these kind of progresses that are made. One very interesting fact, and this probably is um, is a nice way to look at it. How or to answer the question, how fundamental is quantum computing itself? And if you probably take a investment by government, and these are investment by government. These are announced investment in their annual budgets, um, in their specific carve out research and development or education funding. Everywhere in last 1 year, there is a committed fund for evolution, R&D, maturity of quantum computing. Probably this is very, very, if you see, try to analyze a similar graph, of course, because, barring the development maturity of different countries, to 1960s, you will find similar kind of funding allocation for classical computing. That is a very interesting fact because what happens is when government allocate funds in technology maturity quite early in the cycle, that means that there is a seamless diffusion of this innovation that will happen once these are mature to different sectors, education sector, to industries, to services company, to all the sectors that we talk about. And that means that there will be lots of thrust on the diffusion side of the technology itself, not only the innovation and development point of view. So it's very interesting to observe that in last 18 months, almost all the developed economy or emerging economy, they have recognized that this is something that is not very far-fetched 50 years in the future. It's the right time that we put the money muscle behind it that gives an edge in terms of evolving these technologies and making sure that these are ready for diffusion. So it's quite heartening that India is also put almost $1 billion in their annual budget towards this. But having said that, uh, have we already achieved, um, or is there any real robust industrial scale device ready? Probably the answer is no yet. Um, it's it's sometimes you get to hear that it's there, it's not there, it's there, it's not there. Um, so I think the right point of view at this point in time, what I can um, talk about is I think there is no denial that there are qubits available. Maybe there are not hundreds of them, and there is a definite way to look at some fundamental property or start preparing for that kind of computational capability available. Probably a hypothesis based application mindset which says that okay, what if suddenly tomorrow we have got 1000 qubit? What do we do with it? Are we ready? What are the implications that will happen? What is the preparedness that we have to do to really start making use of that? What if I have only one qubit? Can I use the fundamental property of those qubits to really do something? And in next few slide, I'm going to cover some of those use cases that we are actually working with clients. Some of those are basically uh, trying to figure it out how these things will work. Very interesting use cases that we are working with them. This is the kind of conversation that we are having in terms of application use cases. Some of these are very well-known optimization problem, weather forecasting, encryption. One of the kind of early proof of concept that we are trying to do is what will be the um, world of blockchain, or what will the future of blockchain in an era of quantum, because probably we all know that it's quite debated that once quantum kind of algorithm is available in encryption based communication will have to have a little difficult life. So these are the kind of investigation that we are doing in terms of use cases area. But I'm going to talk about three use cases in a specific that we are working from different sectors. One is banking, and this is a use case that is actually getting translated. There are lots of funding behind this use case. There is a startup that is driving the implementation of this use case. What happens in portfolio allocation, traditional portfolio allocation in finance, is you have different kind of assets, investment instrument, and then you try to identify a portfolio of that asset based on the risk quantification, or how risk averse a guy could be, um, and that's how you construct a portfolio. What is the expected return and things like that get associated with the risk. However, the way that these algorithms work, if your space or the asset class becomes very high, or the asset property, if you want to dynamically change. So, for example, if you have an equity of company X, and how risky is that asset change very dynamically, right? So what happens is if you increase the asset whether equities or bonds or different, or increase the dynamics in that, or you try to include the equity across a real global mutual fund, say for example, if that is the question, then the space that you have to explore becomes very, very high. That's one side of the equation. Second side of the equation is, let us say, right now, traditionally speaking, the kind of risk bucketing for a particular client set is very fixed. Maybe there are 10, 12, or something like that in asset industry. But everybody has a different risk profile. So what if we create some kind of a game simulation, and we really identify a machine learning logic to identify the real risk factor on maybe 1,000 bins. Now, what happens is when your asset bucket and your risk bucket becomes very high, it becomes a so complex problem that traditional classical computer cannot solve that asset allocation problem. So what is happening is, in this specific use case, what we are working with an industry and a startup, and there's a funding that's going on behind this, is how we can use quantum computing to really solve this portfolio optimization problem in a very fine-grained basis. This is something that is actually going to really has, it has the power to really change the dynamics of entire portfolio allocation industry itself. And this is something that definitely many of the finance companies are thinking about trying in their own, and find out how quantum can really help in this. The second use case is a very interesting use case, and this use case is coming from a casino industry. Now, this is not about how many qubits you have got. This is using a very fundamental property of randomness. Now, we all know that if any of you gone to casino industry, uh, uh, the nature of that industry is all driven by randomness, and there's a constant struggle, or the entire business, or revenue is driven by, can you reach a perfect random generator and avoid getting hacked, and don't lose lots of money to hackers by giving them clues, um, and they win the jackpot all the time. So what happens is, they use pseudo random generators in their slots machine, in different kind of derivation of the slot machine to emulate games. But one of the things that we were trying to do, and we are still in working with the company, is, can we use the perfect randomness of a single qubit to generate that kind of a behavior in a slot machine? And if you go to, I think there's one Australian university which actually has a site to give you a perfect random generator. You can go to that site and see how does it uses the property of quantum qubit to really generate a perfect random. So this is a very, very interesting and quite innovative use case application, where it's not about the capability of computing, but it's a capability or a specific property of a single qubit to go and start using that in an industrial application. The other use case is also in POC stage with us, with one of the banks that we are doing, and this is all around anomaly. Fraud is a kind of anomaly. We probably all reconcile. Um, but what happens is there are when we talk about anomalies, there are various dimensions that pops in. So what we did is we try to combine the power of you know um, machine learning autoencoders and restricted Boltzmann machine and things like that, energy based model, and try to do quantum machine learning kind of situation, uh, and see whether there is an implication of that kind of a thing in real world scenario. Um, so we actually use this on IBM framework, and it's definitely showing early sign of result. The key difference is the number of data points and the variables that you can increase in different kind of anomaly detection situation that probably becomes very, very difficult in the classical world to really provide so much kind of variability and dimensions to really do a quantum machine learning kind of a situation. So this is another use case that is we are working in. There are quite a few use case that we are working in other industry. Route optimizations definitely. Everybody is trying to find out. We're also working with one of the drug um, company to really see whether some of those things related to chemical promising capability of quantum computing, chemical application, drug discovery, those kind of a thing can also happen. But yeah, all these use cases are giving early sign, um, and uh, and definitely a leeway to really realize what can quantum bring in real time business value. Um, so I'm going to take a couple of slides to really see what we learned from this and what is our point of view in terms of adoption. I think the two ways to look at it is one is definitely the maturity of the technology itself. The second way to look at it is how it will evolve for industry readiness. And in our point of view, it will be completely ecosystem play. And I'll come to that. What do I mean by that? But it will not be just a hardware uh, success. There will no Eureka moment where you have a hardware success and you are done. That's not how it's going to happen. What will happen is for any such kind of innovative and groundbreaking technology to really get into the industry, there will be a wide lens perspective that will come in play. Entire stack of innovation. I think yesterday you had a little bit discussion about kind of API and things like that. Everything will happen at the layer of the full system architecture. The thing is that we all always have to remember, and I think parents started incubating artificial intelligence in in 2015 when it started getting out of their its winter. Is that how it will actually work in real system way? What will be a software life cycle of it? What will be the DevOps probably of this? I think those same very question will be playing out in this world also. And um, if you see the investment or kind of innovation or companies that are getting formed, these are the these are the these are the companies which cuts across the stack of it. Probably one of the early kind of consulting assignment we did with one of the largest bank is they were saying that look. Assume that we have already a quantum computer. Um, what I will do with it is it one question, but how I will do it? Do I have the resources? What will be a JD of a quantum engineer look like? What will be a software lifecycle will look like? How will he actually get access to that? How is going to write a code for that? How is going to test? Will it change? Will the engineering discipline change? Will the kind of testing metrics that we use today before we launch a system change? Will the reliability criteria change? How do we assess that? So actually, we did a consulting assignment to see various aspects of it, and that's kind of drills down to our point of view that quantum adaptation in industry will be a full stack system architecture adaptation, and that opens up a different dimension altogether because there are opportunity innovation in all areas of stack that will happen, and that is where the real diffusion will start happening in the industry. So Sasank asked me very specifically that after saying everything, given that this is a mostly a student-driven workshop, how a student can really get benefit of this? How does he find the true north in this revolution? Um, I'm I'm quite sure that some of you are already doing something around it, or maybe doing some project, some doing some research or something like that. But here is my take, right? Um, I think research is definitely one thing that we can pursue. And in today's world, the research doesn't become pure research. There are lots of uh, enterprise sponsored research. Some of them we have listed there. That is a combination of understanding the theoretical innovation as well as industry adaptation. That is definitely one angle that lots of investment, lots of focus, and lots of career options are available. I think the second is definitely joining an existing enterprise and seeing how they are working. There are quite a few of them. I've listed a few of them. Um, and what to say, definitely one of those company which is from servicing point of view, we are in early co-creation mode with our clients to really support this innovation. And hey, there are lots of opportunity to startups, and I'm sure that there are quite a few incubators across the globe who are looking for some bright ideas across the quantum ecosystem, quantum stack, and really eager to see whether they can be part of this game. So um, don't rule out that startup is definitely a very good idea. Um, so to speak, there is no Kaggle today for quantum computing. 3 years back, there was no Kaggle for artificial intelligence, probably 4 years back. But Kaggle is like go to place for artificial intelligence today. Uh, as basic as that, to really do some experimentation in quantum computing is not available. Uh, there is no data set. There will be change in the data set itself. Probably there will be a pipeline to ingest a data set because all the data set right now exists is in digital world. What will the corresponding data set before you give it to the quantum computing device? So there are lots of areas that startups are coming up, and there are lots of areas where probably incubators are really looking into, and how they can be part of this portfolio. So yeah, in my opinion, this could perhaps be a good point to start investigating different avenues where one can really get into this this revolution. So I'll stop there. I hope I met my time. And back to you, Sasank, if any questions or anything else that you want me to cover.
Right. Sir, I have a question that as you mentioned,
Hmm.
the pattern of investment across countries has been digital has been similar to how digital computers were invested in. So, if we are using the same trend, can we say that the usage of quantum computers will be quite common in the future?
I think I think the probably the right perspective to look at is a class the way that adoption or probably how to availability of the computing power uh, will be different. Say, for example, if you look even classical computing, right? Um 10 years back, how we used to access a heavy device. Everybody has a data center, right? Everybody has a supercomputer. Everybody has this, that, everything, right? But today, the computational capability, the availability of computational capability, you can have through cloud. Just think about it. So, although you don't own a computer, the computation capability is probably infinite for you today. In just a what all you need is a laptop and a nice working internet. So, in my opinion, I think the the way that quantum computing probably will get accessible may have a different trajectory. Uh, who knows? Maybe there's a different shape of cloud that will pop up, or maybe there's something else. But yes, it will be available to once it goes to a quite a mature state. It will be available. Otherwise, there is no way that you have lots of um, so-called innovation in application. That's point number one. Point number two is I think probably the application, the real value of quantum computing comes in a very complex scenarios. So at least in near foreseeable future, probably classical will still be there, and it will be there for quite a long time, in my opinion, unless until there's something really different happen. So yeah, these 2 points are going to probably play a critical role in how quantum will be made available to everybody.
Okay, so sir, I have a question. Uh, so,
Hmm.
how do you think quantum computers will impact AI? Like, in what way do you think would be the like next breakthrough in the field of AI or deep learning or anything?
I think quantum machine learning is definitely one very active field of investigation, and fundamentally, if you think about it, machine learning always work on you know kind of the more you data you give, the better algorithm. And it's all boils down to very simple thing is how fast is you are calculating your error in as much space as you can go, right? And of course, overfitting and all this kind of thing that we probably we all know we have to do. But fundamentally, it's all about computational capability in a higher dimension of data. So that is one aspect that definitely quantum computing is going to help. Second is some of those hard bounded problem. Say, for example, the operations research kind of problems. Now, if you start thinking about operations research kind of a problem, um, those problem are not right now formulated as a learning problem. Though those are very bounded optimization problem. But when you start going in quantum machine learning dimension and start investigating that, what happens is there is a way to reformulate those problem as a very high space learning problem, and then you can start applying and converting those in a learning situation. For example, uh, many things are discussed about route optimization, right? At the same time, many times it's discussed about that put every truck, delivery truck, or maybe every container, maybe every shipment in IoT connected. Now think about it. Route optimization, as it is a very hard problem to solve. Now, suddenly, what you have, if you connect every device, you get lots of information. What are those information for? They give you more options to do various kind of routing. So what actually happened is you went from a problem space, which is as it is a hard bounded problem space, and you gave you more variables, more options, and it became even more harder problem, right? Those are the spaces where quantum machine learning will definitely create impact. This is a very active field of research also in quantum machine learning, and I personally say that some of you should definitely investigate how that is evolving, and you will find quite interesting and quite exciting ways that researchers are driving this field. So yeah, it's going to have a quite a interesting combination of quantum and machine learning.
Right, sir. Thank you for this lovely session. It was very knowledgeable to us all, and I wish the best of luck to you.
Thank you,
Thank you.
and thanks for having me. And best of I give all the wishes for your next session.
Thank you, sir.
Thank you. Take care.
Like participants, we will be having our panel discussion at 3. So please stay tuned. We are waiting all for all the panelists, and then we start the session. Why, Mr. Arpit? I believe you're muted right now.
Yes, I am. Can you hear me now?
Yes, you're audible and visible right now.
Okay, perfect. Good afternoon or good morning. Actually, it's afternoon, so good afternoon.
Good afternoon.
Uh, just a
We are just
question. Can you see the background as like straight? Because when I look at it, it's
yes,
something.
it is straight, sir. We have
It
checked it.
it
It is
flipped.
straight.
Okay, perfect.
Right now we have Ms. Supriya Nayak, other panelists, and as well as Mr. Arpit Mehta. We are waiting on two more members. They will be joining us soon.
Hi Arpit. Hi
Hi,
Shashank.
yeah,
Hi
Hello.
team.
Hi, ma'am. I hope you all are doing great. Like,
Yes, thank you.
yeah.
I
So
hope
far
the
so
same
good.
for you.
yeah, tough times.
Well, it's fun time sitting at home.
Uh, I think the students would care to differ on that.
Sure.
Yes, Mr. Rajesh Dudu has also joined us. We are just waiting on two more panel members.
Hey Shashank, how are you?
I'm fine, sir. We are just about to start. We are waiting on just one more member.
Okay.
Hi, Rajesh. Nice to
Hey
meet you
Arpit,
finally.
how are you?
Yeah, so far so good. Just starting. Looking forward for the thing. So, Shashank, it's planned for an hour, correct?
Yes, sir. It is planned for an hour.
Shashank, first of all, don't use the sir and all. My name is Abid. Just
Sure, sure.
use my first name. I don't like sirs and madams and all those like stuff. I mean, for me, just use my first name.
Right.
So how many do we have, Shashank, currently in the?
Right now, we at the time we have around 20 members watching live, and I'm sure
Oh,
come in, come out. So it constantly changes and increases right now. Uh,
okay.
we also have Dr. Kishan Sluja with us. Dr. Sluja, your mic is muted right now. Just
Yeah, good evening, everyone.
Good evening.
Good evening.
Good evening.
right. I believe all the panel members are here with us right now. So I'll just begin by introducing all the members. So let's just a minute. Right. So first, I welcome Mr. Arpit Mehta. He is senior architect in senior AI architect in strategy and innovation at Microsoft, and is based in Germany. He is an experienced artificial intelligence, machine learning, and big data professional. He is also experienced in using quantum computing and for solving complex business optimization problems. He works actively in applied research and has 4 patents and more than half a dozen research publications. Furthermore, he led the big data AI initiatives for Pan BMW Group related to vehicle development and autonomous driving cars. Next, we have Dr. Krishan Suja. He is a professor at UIT Punjab University. He has more than 20 years of experience in research and teaching. His specific research interests includes intrusion detection, protection from internet attacks, web performance, and more. He has published 2 national and 2 international books in the field of cybersecurity, network security, and computer science. He's also published more than 110 papers in national and international journals. Then our third panelist, Mr. Rajesh Thuru, leads the blockchain and cybersecurity practice at Tech Mahindra. Lattice 80 has listed Rajesh as one of the top 100 blockchain influencers in the world, in recognition of his contribution over the last 5 years. Thinkers 360 has recognized him in the top 5 global list of blockchain influencers. He was instrumental in establishing blockchain practice at Tech Mahindra. Under his leadership, Tech Mahindra has been recognized as one of the global blockchain leaders. Various leaders such as and various bodies such as World Economic Forum and governments like state government of Telangana. He has spearheaded the implementation of solutions to block spam calls and text in partnership with three leading telcos in India and Telecom Regulatory Authority of India. For the final member, we have Ms. Supriya Nayak. She is the senior incubator at emerging technology at Virtusa. She has more than 6 years of business leadership experience in the fields of artificial intelligence, quantum computing, digital strategy, ERP development, and she has also been the manager of global leadership cadre at Tech Mahindra. She has done her MBA from IIM Ahmedabad and Toulouse Business School, France, in General Management and International Marketing Management. So I welcome all the panelists to this session.
Thank you, Shashank.
Right.
Thank you, Shashank.
Yes. So I've created a round of questions for all of the panelists, and I'll start the first question with Mr. Arpit. Mr. Arpit, we will be, it's though the session is hour long, we have more than an hour if we wish to extend it. So let me start with my first question for Mr. Arpit. How extensively are you using quantum computing in the field, and how has it impacted the effectiveness of artificial intelligence?
Yeah, so can you hear me? I'm audible?
Yes.
Okay,
Yes.
perfect. So, I mean, from my side, actually, it really depends on on with whom you're talking. I mean, if you look at the whole quantum computing and quantum technology initiative worldwide, it's as of now divided into multiple like stakeholders. There are people who are kind of creating the actual computer, so who are in the more the hardware part of the world. Then there are business people who are trying to understand what kind of problem we can solve with the technology. Then we have in the middle the so to say the algorithm developer, the mathematicians, which are trying to understand the business problem and try to put it on the different type of hardware technologies which we are building. And each computer has a way of working, and hence the math or the way you write the algorithm varies with if you're working with an IBM computer, with a Google computer, with Microsoft Initiative, or the other players which are in the market. So I mean, as of now, there are multiple streams. So one common pattern which I see, at least in the field, say so to say non-technology players, is that they are as of now heavily focusing on creating IP for their organization, because this is a new technology. A lot of players are investing, and it's expensive piece of technology, I will also put it like that. So generally it's big players, global names, global brands who are working in this area, and as of now they are saying, okay, because this is kind of disruptive, they want to create as much IP as possible and then patent those things so that they can then become future proof, or can have like IP which they can maybe even sell or resell while in the future, when the technology become a bit more available to the large masses. So this is where a lot of research is going on. And even the non-tech players, if you go closer, they are generally are coming from academic background, and are trying to, first of all, like trying to create, doing kind of applied research. It's not theoretical in the industry, so more like applied research to figure out how we can solve our current problem better with this technology, and creating and writing papers, publishing paper, including I do that. So publishing paper, writing stuff, and then creating IP, writing, filing patents and whatnot for the organization to create a lot of IP. So this is first of the questions. The second part which you mentioned is how it's impacting the AI. That's a very interesting question, because of course, if you look from the whole technology perspective, there's a whole stream called QML, which is quantum machine learning, or quantum inspired machine learning. Let's call it like that from hybrid point of view. So if you think from the AI side, I mean, I guess a lot of people use AI, and everybody use deep learning or deep neural networks and whatnot. So if you study that, I guess in the deep learning or 101 lecture, you will study about Boltzmann machine, which is restricted Boltzmann machine, which is a very simple neural network, one visible layer, one hidden layer, and it's a fully connected graph. And essentially, what it does is it reduces dimensions, and it's called restricted Boltzmann machine because what it does is it tries to take the input and create and map it to a Boltzmann distribution, which is, again, I'm going a bit more geeky here, but so and the quantum computer, because of its nature, are Boltzmann distribution by default. So it's like, if you think about deep neural network, you can actually just take qubits and then entangle them with each other, connect them with each other, and it will out of the box create this RBM machine, because this is the way nature works. And in the deep neural network in AI, we try to emulate that with quantum computing. That will be the de facto standard. So we can see that dimension reduction. And then the second thing is, when we do machine learning, we split the data between test and train. So we want to train the data, then we want to test the data, and we do sampling of the data, how we can like divide this thing. And the best way of sampling is to do random distribution and figure out, okay, what's the smallest piece of training data I need, which represent my overall data, which is where quantum computing will play a very good role, because it will become also a very efficient random sampler of the data. So this is one place. Then when we go in advanced AI, when we talk about auto encoders in the speech processing and natural language processing neural networks, there it's like autoencoder essentially is again the same thing, which takes the input, try to reduce the dimension. And here also, uh, using quantum computer, what we can do is we can reduce the noise in the autoencoder, hence the error in compressing the information to a shorter like bits will be improved, which is a big problem right now in the neural networks, that the autoencoders kind of induce some artificial noise, which creates the prediction or the AI model a bit not as good as we want to. And with quantum computing, we can improve those things. So the possibilities are a lot. Again, we are still very early because of the state of the machine or technology right now, but I see a lot of things happening in the AI area as well, especially right now in the hybrid way, in which we use both the classical machine learning, and then a piece of it is done on quantum and the piece is done on the classical way.
Right. So the process that can be optimized are done on the quantum machine, and the rest are done on your classical machine.
I mean, just think of it like this. I mean, the quantum computer, so there are two kinds of problem. There is a big data problem and there is big compute problem. So the big data problem, AI, machine learning is efficient to do that. But with the current state of the quantum technology, the quantum computer, the number of qubits, let's call it like that, is not big enough to actually solve the big data problem, because you cannot just fit in this information. So in this case, we are focusing on all this core big compute problem, in which we can say, okay, we will use the quantum like the auto encoder in the quantum computing, because this is where we have less information, but we want to optimize the error to the least. And this piece is then trained on the quantum piece, and then it's plugged back into the classical way. So because I mean, of course, that's not efficient, because you have to jump from the classical to quantum and back forth, which creates some delay as of now. But given the maturity of the hardware right now, that's the best you can do if you wanted to play around with. So the big compute, do it on quantum computer. Big data, do it on classical computing.
Right, sir. Thank you for your answer. Right. So next question that I have is for Mr. Rajesh Dudu. What will be the impact of quantum computing on emerging technology, the IoT and blockchain, etc.?
Yeah, exactly. Definitely. In terms of first to understand the impact of quantum computers on blockchain or on cybersecurity or any of the emerging technology, we need to understand how blockchain or cybersecurity has been structured, right? So if you look at blockchain, there are two things that blockchain thrives on. Why is blockchain becoming active in the marketplace, or why blockchain is preferred by people all over the world? Because of its innate ability that nobody can manipulate the information. The data manipulation in blockchain is next to zero at this point of time. And that functionality of inability to manipulate the data comes from two further functions. One, what is called as asymmetric cryptography, and the second one is called hashing. So if
Right.
you look at asymmetric cryptography has a separate key. It is called as a public-private key pairs, where the key that is used to encrypt is different from the key that is used to decrypt. So the
Right.
asymmetric cryptography came into existence by three people who have come up with a cryptography standard called RSA. Before it came, it was all about AES as a cryptography standard was very prominent. Now, if you look at RSA and how RSA has been structured, so all these cryptographies in terms of the private and public key pairs, they're based on what we call as the trapdoor functions in mathematics. So the trapdoor function in mathematics works in such a way that a classical computer can do the calculation one way. But if you want to do the calculation the reverse, it becomes very difficult. So if you look at cryptography, it all depends on finding the prime numbers. So for
Yes.
example, if I take two large prime numbers and I ask a classical computer to work out in terms of what the output is, it will give me an output which is XYZ. But if I
Right.
ask the classical computer to predict the input that went into XYZ, it becomes very difficult. And so
Right.
is the case with prime numbers or integers or logarithmic tables. And that's how this cryptography has been structured. And now I bring in an additional concept called the Moore's law. Even if you apply Moore's law, where the cost of compute will go down exponentially, and if I apply that onto the classical computers will not be able to break this particular algorithm. Now
Okay.
comes two gentlemen. They are called as Shore and Grover. So
Right.
Shore and Grover have come up with their own algorithms, and then they said that if you factor these algorithms, then you can break that particular cryptography. So the
Yes.
algorithm, which is relevant from an RSA perspective, is the Shor's algorithm, which kind of reduces the number of searches that needed to be done to break that particular cryptography. And
Yes.
that's why now they are saying, since the Shor's algorithm can be executed by a quantum computer, Shor's quantum computer can break the algorithm, and blockchain, which is based on asymmetric cryptography and hashing, will be compromised, which is not in reality it is not. Let me go into the details. Now, if you look at hashing in blockchain, it is based on SHA-256 protocol. AES also uses the same kind of protocol. And to this particular protocol, if I apply Grover's algorithm, what is
Right.
Grover's algorithm is going to do? It is going to bring in a square root impact. That means if I take SHA-256 and then apply Grover's algorithm in quantum computers, the power of SHA-256 becomes SHA-128. So it
Okay.
is basically having the impact 258 or whatever the higher versions which are there. And if you
Right.
apply Grover's algorithm and then do it in the quantum computers, it is going to have the impact. So I have one data point which I would like to present. Even after quantum computers come into the picture, currently we are talking about, even if you take Sycamore of Google, you're talking about probably 100 qubits. You're not talking about greater than 100 qubits. And then if you take the logical qubits into account, the number of qubits are very high. And if I
Right.
apply the impact of quantum computers, and I mean on these particular algorithms, if I look at Shor algorithm on RSA, you need a logical qubit of 2050 and a physical qubit of 8 to the power of 10 to the power of 6. And when you get to that kind of logical qubit of 2050 and a physical qubit of 8 to the power of 10 to the power of 6, the time taken to break the system is 3.58 hours. And if I scale it up to a higher key length in RSA, which is from 1024 key size to 4096, the logical qubits that are required are 8194, and then 229 hours are required to break this particular algorithm.
Right.
And physical qubits which are required are, hold your breath. The physical qubits that which are required to break this algorithm are 11 million physical qubits. And today, and
That's
today
a
we
lot.
are what we are at about 100 qubits kind of a thing. So theoretically, if I get to a 11 million qubit kind of a quantum computer, then I
Then
can compromise
think about that.
RSA as an algorithm. Okay.
Right.
And basically, the guidance from NIST is that to prevent this, move to a PQC algorithm.
Right.
It is available. The PQC algorithm is not available. So some quantum equivalent to 11 million qubits, RSA
Right.
gets compromised. Now let me cover hashing. With regards to hashing, as I said before, Grover's algorithm is applicable. And to break the Grover algorithm, I need
Right.
2.23 million qubits. 2.23, I repeat, I need 2.23 million qubits. And even with 2.23 million qubits, the time that is required to break this is 230 million years. 230 million years. Probably
So
I will be taking 230 births if you believe in Hindu system of cycle of births, right? So in terms of that is the level at which these algorithms are insulated. Finally, all of us get paranoid. This is paranoia that is going to be created, saying quantum computing is coming, blockchain will be compromised, every damn thing in life will be compromised. No, not really, because I've just demonstrated to you the math and also amount of physical resources and the amount of time that is required to break into these algorithms. You can brute force the attack, you can put whatever compute power, it is not going to be compromised. Having said that, my point to everybody is, if quantum computing is used to compromise these systems, what prevents quantum computing to be used to secure these systems further? Why should it go only in one way? If you look at a company called Q New Labs, which is based out of Bangalore, in terms of I have deep conversations with these guys. These guys have already come up with a quantum router, and then they're basically securing information on an optic fiber with quantum routers. So you place the quantum router at one end of the optic fiber, and you place another quantum router at the other end of the optic fiber, and they've been able to
right.
demonstrate it over a length of about 150 kilometers today, and it can expand
Right.
even further. So what I'm trying to tell the audience is, in terms of, it is good to be sensitive to the fact that quantum computers can compromise emerging technologies, but it doesn't mean that they will end up compromising the emerging technologies, whether it is blockchain or cybersecurity. With that, I will turn it back to you, Shashank.
Right. So thank you for that explanation, sir. Now we'll go further into cybersecurity with Dr. Krishan Suja about the question: will quantum computing be a bane or a boon for cybersecurity?
Yeah, thank you very much, Sashank. You see, a lot of background has been already put up by Mr. Rajesh Dudu. So that way, I will say that in terms of cyber security, I would say that I would like to start it from the point that what are the weaknesses in our current systems because of which a lot of attacks are possible. So even if we look at our society and we see the evils and whatever problems that are there in the society, then the major cause behind that is basically asymmetry between intelligence and resource.
Right.
So wherever in the society there is asymmetry between intelligence and resource, there will be problems, there will be thefts, there will be criminal activities, and there will be other sabotage and vandalism kind of activities.
Right.
Similarly, if you talk about cybersecurity or if you talk about the security of the internet, so if you look at the original design of the internet, then you will find that there is a lot of intelligence and resource asymmetry over the internet. How it is like that? Because if you talk about internet, at one end you have a source, and at the other end you have destination. Your source can be a simple computer system or mobile device, and your end device can be, or end machine can be your server. So at the ends, you have got all the layers. Whereas if you talk about the middle portion of the internet, it is consisting of fast communication links and the fast communication devices. And these devices, they are not having all the layers embedded in them. So
Right.
the intelligence part is at the ends and lot of resources are there in the middle. Now the middle part is not intelligence, whereas the end part is not having lot of resources. So that way, there is a lot of intelligence and resource asymmetry. So this is exploited by the intruders and hackers or attackers. Why? How they do it? They are basically able to capture the information in between, and they are able to do some analysis on it. And even the information which is going through the internet, through the communication subnet, which is full of your fast communication links and your networking devices, there the information can be captured by the attackers, and they can craft their own packets and then can compromise the integrity of information that is moving, that is the packets that are moving from one end to another.
Right.
So that way, a lot of attacks are possible as far as our internet is concerned. Now, in order to address it, there are various aspects in security, as Rajesh Reddu has already explained in detail. So I'll a little bit touch, keeping in view my first year students are audience in this particular discussion. So from their point of view, I'll just like to highlight that there are three main aspects of security. One is confidentiality, another is integrity, and third is availability. Now, in terms of confidentiality, what we do is we try to encrypt, or we try to scramble our information at source and send this information on the information highway or on the communication subnet, and we do it in such a way that unauthorized users are not able to understand it. This is what we mean by confidentiality, and it is achieved with the help of symmetric encryption algorithms as well as asymmetric encryption algorithms. So already Mr. Rajesh Dadu has explained about it. In symmetric, the commercial solutions are based on DES and AES based encryption algorithm. DES was the older one. AES is currently being used in the commercial applications. Whereas if you talk about asymmetric encryption, there RSA is playing a big role, and then ECC is also playing a big role as far as our asymmetric encryption algorithm is concerned. And if we want to achieve confidentiality and integrity both, then we need to use best of both the worlds, like symmetric as well as asymmetric. We do, because symmetric encryption is almost 100 times faster than asymmetric. So what we do, we share the key with the help of asymmetric encryption, and we do encryption with the help of symmetric encryption algorithm. So there, as Mr. Dadu has already explained about asymmetric encryption like RSA, based on the Shor algorithm, what we can do is we can exploit these quantum algorithms for the purpose of breaking the big number into different factors. So factorization problems become quite easier with the help of Shor's algorithm. As Mr. Dudu has already explained that 11 million qubit processor is required to break it, as far as the current state of art in this particular RSA-based encryption is concerned. So, so to reach up to 11 million qubit processor, I think it will be a long story from this point at least. So we can say that yes, there is no doubt in future there will be challenges to cybersecurity in terms of these encryption and decryption algorithm, because ultimately you see, when you talk about a key, whenever you talk about a key, brute force attacks are always possible. And if you talk about 512-bit key for symmetric encryption and you try out all the possible combinations, then there will be definitely a stage where where all of these combinations can be tried out with the help of quantum computing. Because quantum computing, because of the superposition principles, has got very good strength in terms of doing the things in parallel manner. So in future, we can say that there will be challenge towards these encryption algorithms also, and that's why already research has started in terms of quantum proof encryption algorithm. So nowadays, people are now working in lattice-based encryption algorithms. This is the reason behind this, that the quantum computers are very fastly, coming into the market, and they are posing a big challenge. So in that way, whatever existing algorithms are concerned, definitely they need some modification. Maybe not now, but in future definitely they will be requiring. But on the other side, if you look at the integrity aspect as well as this integrity aspect, there, if anybody tries to modify the information on the way, this is actually stopped by quantum a kind of mechanism. If you make use of a quantum key cryptography or quantum key based encryption algorithms, and by that way, if you do the transfer of information, in that particular case, if anybody tries to measure, if anybody tries to snoop information in the middle, or if anybody tries to modify the information in the middle, it will be a big problem. So that way, I will say that it is a boon for cybersecurity. Uh, if if in future quantum cryptography will be used for the purpose of communication also, so there integrity as well as snooping, integrity attacks as well as snooping will be very difficult to implement. Whenever anybody tries to measure the things in between, at that particular moment only, center of the or originator of the information will come to know that somebody is trying to play some mischief as far as the overall communication is concerned. So that way, it is a boon for cybersecurity. So, in terms of this, I would like to say only this much. Yes, over to you, Shashank.
Right. Thank you, sir. Thank you for this nice explanation. Next question we have from Supriya Nair. Quantum computers are very new in the industries, so how are companies adopting it? And how are they using it to start their business in this direction?
Right, Shashank. Uh, so in our previous session, we have seen about the quantum computing stack, right? We have hardware, we have control system, software, and then
Right.
services. So I'll pick up with the software and service industry. There are a couple of things which is happening at a very rapid pace in this industry. First is conversion from classical to quantum algorithm. Algorithms. A classical algorithm which are currently being used by classical systems. Classification which are being used by Netflix or Amazon. Logistic company uses their fraud detection algorithm used by banks. They are speech use Google analysis and video analysis which is being correct. So these are the classical kind of problems. Here we can think that okay, fine, all these problems are being smoothly executed by the companies. We as a customer for such kind of, well, the one which I mentioned, any features which the features which these products can be built, give it large pool of data in small amount of time. For example, currently we can do text analysis of a PDF, but the classical algorithm faces a lot of challenge in text. Similarly, Alexa and Google, they're still learning the speech analysis. they are not present in all languages, and also they still need a lot of data to be more intelligent. Even for root of the current algorithm have been so efficient, then why Amazon is still taking time for delivery. The frauds, though banks are able to identify fraud, example involving two back-to-back transactions which are happening from a different bank, detect frauds which are made by big billionaires. So here we can see that though good, but they need a lot of improvement, and that into quantum algorithm. And this is one of the first step which is being software is like here for us to implement to a quantum processor. So this is the first one. Second point which I mentioned computers, it is not necessary that it is always there are many algorithms in which classical is better than quantum. For example, say when we do multiplication of large numbers, quantum keep on shedding its previous get the result. But it is not the property of quantum. Quantum cannot shed information. So the algorithm has to be changed here. And because of this, new algorithms has to be developed. So these are a couple of things which service or software industry are adopting it into the business get started with quantum.
Right. Like view of how how they are not in quantum computers. Right. So next question I have for Mr. Arpit. I know from reading your project documentation and self-driving cars. I have a question about that. That as part of your previous project in self-driving cars, how they're working in the field, and also solved optimization problem in multiple robot systems. So can you shed some light about that also?
I mean, I guess you asked about because again, it's another cool technology. But
Yes.
I mean, from the from the outset, from the quantum, as I said, not like straight implications on how we can how we can in a couple of years, not in 15 years from hence from now. So we need a bit more mature technology to do that. But a couple of points which also Supriya touched was like in terms of application, where we see that there's a straight demand which will also be used for autonomous driving as well, which is routing optimizer. So like when you kind of call a Uber and it says I'm finding a driver, near you, so they go over. So as a we can use this let's call a location problem. So whenever you have n cars, you have which customer should be assigned to what car based on different criteria. It's a multi-criteria optimization problem. This is where we think that it's a big compute problem. It's not a big data problem because all we have is distance between people and different locations and that ETA at earliest time of arrival and whatnot. So the number of data set is less, but the number of possibility to have a so these are the perfect examples where we think that it's a big compute problem. We need a lot of compute power to solve this problem, and hence these are like the one which are the natural fit to be done better on the versus as compared to the classical one. So this is where I see, like, for example, one of the cases encryption and the one. I will will give it a different the autonomous driving car, and of course it will be expensive piece of technology. It will not be a cheap
Right.
car, let's call it like that. And
Right.
we think that this car will be available in the market in say 3 years from now.
Right.
And if you buy a car from a premium player like Daimler or Mercedes or Tesla and whatnot, so the guys who are actually trying to build these cars, BMW and whatnot, when the car is launched, they say that the car is generally have a lifetime of 15 years,
Correct.
which means we are talking about 3 plus 5. We are talking about somebody using this car maybe in 2035. Let's call it like that. And
Right.
with the kind of money and the effort is pushed into this area, we will see that we will see radical improvement. And of course, not everything is in public domain. Even I cannot share what Microsoft is doing. So let's put it like that. So there is a considerable amount of effort and energy being pushed into this area. So I would not really shut it down that say, hey, forget about it, we don't have to worry about it, because even if we say that we have a good decent sized computer in 10 years from now, when this is available, that self-driving car is not secure anymore. Because what we have to do, we are building a car now and we are encrypting it with say RSA for its internal communication. And now a hacker, say 10 or 15 years from now, is able to hack that internal communication between the ECUs of the car. You can actually make it like as they show in Mission. If you see Mission Impossible, Rogue Nation, last one, not the current one, the previous one,
Okay.
they killed the president of the country by just controlling the cars on the street. Of course, it's
Yeah.
sci-fi right now, but
Yes.
but in 15 years that would be reality when the autonomous driving is there, because you're not driving. The car is a big computer; it's driving on its own, and if somebody can hack into the network, then you are dead basically. So,
Okay.
and I know a lot of people at my ex-employer and also in my current job who are actually working in PQC, the post-quantum cryptography algorithm, and we are already looking into, okay, what we have to build in the car and push it into car now in the next couple of years, which are quantum proof even 15 years from now. So there is some effort, because we cannot just simply say, okay, let's hope that the humanity will not excel at the speed which we excelled in the last 15 years and assume that we will not have a million qubit computer. Maybe we have in 10 years or 15 years from now. And if that's the case, then that car is not secure. And I will not really, and then if you are a product development company, you want to make sure that you are not selling a killer machine to somebody, because there's a big brand impact associated with it. When Tesla or Mercedes or BMW is selling a car and they promise that you can use this car for 15 years, we have to make it secure for the customer until 2040, and
Right.
this is a hell lot of a time from now. So
Right.
I would say we have to really work into this problem as well, because
Right.
not everything is IT. I mean, this RSA is used everywhere, and of course IT is the easiest piece. The difficult piece is when you go into the manufacturing world, where they're using in IIoT or in cars and in electronics equipment where they're using encryption. They also use the same technology, and this is where the bigger problem of the whole encryption and security lies. So I would really focus on that one. Now going to the second one, actually, I guess we will go over the time for sure. I can
Right.
spend another half an hour as well. So the second topic which you talked about is essentially what I wrote a paper and a patent about in
Yes.
my past job. It was about optimization problems. So just to give an idea, I guess majority of the people, I hope, have seen how a car is being made in the plant. So you have like this big plant and there are robots coming from everywhere which are doing painting of the car and welding the joints and all. So if you think from a mathematical point of view, and this is what the beauty of mathematics is, that if you think from mathematical point of view, a, a, a robot which is doing the painting of the car, or a welding robot which welds the metal joints in the car, is actually trying to solve a routing optimization problem, similar to what Uber is trying to do on the street with the car as well. So if you
Right.
look, if I write a math of both the business problems, it's more or less the same. So
Right.
what I tried to do was, we have 6 robots in 3 dimensions which are given a task to weld the welding joints of, or the metal joints where the metal piece in the car body is, and these seams are could be a few millimeter until a few, let's call it more than 2 meter long, a welding joint, and these are in 3 dimensions and there are 6 robots. So my work was how we can use a quantum optimization algorithm which will then find try to solve two kind of problem. The first problem is we have say 300 welding joints which we have to weld, and we have 6 robots. So what's the efficient way of dividing this 300 seams into 6 robots so that they can finish the task faster. So if you think from mathematical point of view, that's graph division problem. It's an NP hard problem. Even quantum computer will not be most efficient in doing it, but we still can try to optimize it. So that's the one part. When you
Okay.
go to the second one, in which we have now 30, let's call it, we divide did a split, we have now 30 seams which every welding robot has to weld. Then all it has to do, what it has to do in classical is a traveling salesman problem. I guess you all studied that in your in and we know it's an intractable problem for classical computer. Traveling salesman is not solved yet.
Right.
So what we are trying to do is to understand how we can use the quantum annealing algorithm. So this is where I use the D-Wave annealer machine to come up with a faster solution so that we can optimize on 3 levels. So first of all is the time, which is the most important thing. The faster we can weld the car, the more car we can produce. And if to give an idea,
Yes.
the number of cars a premium company sell is restricted to their building capacity. So if they can make more cars, they can actually sell more cars. Then then the
Right.
second problem is the efficient use of material, because if you think that this welding material, this robot is going, how what's how we can efficiently use the material. And the third, I would say the most important after time is is the life of the robot itself. Because what happens is, like, this seams could be like a small 2 centimeter seam, it could be a 2 meter long seam, and every time a robot goes, it goes at acceleration and then it breaks, and then it goes again, accelerates, and then it breaks again. This creates a lot of wear and tear on the robot as well, because it accelerates and deaccelerates and stops and breaks, which is not good for the robot's life. And I can tell you, these are expensive robots which are fully automatic working. And if god forbid, if this breaks down in the middle of the assembly line and the assembly line has to be stopped, I will not go into a number, but like, it's a public information. If an assembly line of BMW group one plant is stopped for one day, it costs them 50 million euros. So they are talking about big money when they
Yes.
when they talk about assembly line. So they have to make sure that we can optimize the robot life as well, because A, robot is expensive, and B, it's even more expensive to stop the assembly line for building this car. So these are the different problems for which I tried to basically then use the quantum annealers to come up with the algorithm which can then optimize these two problems, and then we implemented this thing in our research project.
Okay. So thank you for that beautiful explanation. To really put the new perspective in my mind of the
So that's
quantum.
why I say, I mean, when you study second year algorithm, it's gonna bug you until the end of your career if you're really in professional sciences. I can tell you, this
Okay.
traveling salesman problem is still my problem, even after 15 years from graduation.
Yes. Thank you for that explanation. Right. So, right. My next question is for Mr. Rajesh. That how has quantum computing affected the blockchain technology, and if its effectiveness, if at all?
Yeah, Shashank, I covered it in my previous explanation, right, in terms of how it is going to impact the blockchain technology, at least from a claims perspective,
Right.
from a perspective of cryptography and in terms of hashing, and both are insulated until and unless significant developments happen in quantum, which we are not able to predict at this point of time, or the quantum computing scales up exponentially, much against the conventional thinking or the thinking that people are currently expected. I don't see it having an ability to impact the blockchain technology, at least in my lifespan, or at
Right.
least in the next 3 or 4 generations. But there's a lot of hype that gets built around, a lot of media just to attract attention. They say that blockchain has been hacked. So many cryptocurrency exchanges have been hacked and stuff like right. The
Yes.
analogy is somewhat similar to this. An app gets hacked. Internet never gets hacked. Nobody says internet has been hacked. It says an application on internet has been hacked. Exactly, it's the same analogy with respect to blockchain. All that cryptocurrency theft that you have seen, they are not because they have compromised the underlying blockchain technology, but what they
Right.
have been able to compromise is the infrastructure on which that blockchain technology runs. They have compromised the credentials of servers. They have
Right.
compromised credentials of applications using phishing and social engineering. They have
Right.
compromised those cryptocurrencies. Now, if people are vulnerable to phishing, no matter whether he is a quantum expert or using tools that are enabled by quantum, and if the guy has been phished and that results in vulnerabilities, quantum cannot contribute anything anymore
Oh,
until and unless you're going into an era wherein you're completely replacing password-based authentication. People are already talking about zero knowledge proofs, where blockchain is using zero knowledge proof to a major extent. Z currency, cryptocurrency, used it for the first time from a zero knowledge proof perspective. And people are also talking about authenticating without passwords. When it gets to those kind of a scenario, yeah, then everybody is insulated. But the compromises that have happened till date, and which are to be claimed as the compromise of blockchain technology, I refuse to believe.
Right. Thank you for that answer. So I have the next question from Mr. Dr. Christian. How can universities and college encourage students in taking quantum computing as a career?
Okay. Yes. Yeah. I think first of all, awareness regarding this has to be created, and this workshop that you are doing through this, through these kinds of programs, awareness can be created. And second effort, I would say that we should, have some kind of quantum computing related subjects. So though we are not having a lot of experts with us in this particular field, so that way I would request through this platform only to Arpit, Supriya ma'am and Mr. Rajesh that you please help us out in providing the faculty resources in terms of teaching these subjects. So we can offer these kinds of subjects as our electives. So accordingly, this way, more awareness and more fundamental knowledge in this particular technology will be available with the students. And I would also say that since we are not having a lot of resources in terms of buying the equipment related to quantum, so that way, some kind of simulators, if somehow they are available in the open domain, those simulators can be, utilized for the purpose of experimentation. And then IBM, I think IBM Cloud, on the IBM Cloud, some kind of
Yes.
resources are available. So that platforms can also be used by our students, and awareness regarding this can be given to all the students that they may use it for the purpose of learning. And some programming languages or tools are also available on it, and documentation for that is also, I think, available on the internet. So that way, students can start working. Not only on the hardware side but on the programming side also. But for all of this, I would like to take guidance from you experts that if somehow you guys can help us out in rolling out in our universities. Yeah.
Yeah, absolutely. Sorry, Shashank. I just wanted to respond to what Dr. Krishan had mentioned. I know Arpit is from Microsoft. Microsoft is also one of our valuable partner. But I've seen this being enabled more from IBM perspective. IBM can give you a 5-qubit simulator at this point of time. And if you're looking at more than 5-qubit kind of a simulator, you can go up to 20 qubits kind of a simulator. And we are very, very happy to facilitate that for you, Dr. Krishan. I'll personally speak to my contact at IBM and we will contribute towards that, number one. Number two, at Tech Mahindra, we have what is called as a Makers Lab. To give you a perspective, Uber driver in Pune came to our Makers Lab, learned Python, and developed 4 to 5 applications in Python. So we can extend that Makers Lab to your students. We have set up the Makers Lab as far as Tokyo recently, and we can give you an extension of that Makers Lab where you could use it for AI, blockchain, cybersecurity, data and analytics, IoT, and the other emerging technologies. We are very, very happy to facilitate that and contribute that from Tech Mahindra side to your university.
Thank you very much, Mr. Rajesh. So
I'll,
this
I'll
is
just
the
I will also add just from my side as well, because you mentioned about IBM. Of course, like they're providing a physical access to their what they call the Wilson Tower IBM machine, and it's a difficult one. I will actually give a different spin off, which I actually also tried. So if you go to Microsoft, just type QDK, Quantum Development Toolkit. It's a simulator. Just download it. On a normal computer, which I guess everybody has, you can simulate up to 7 to 8 qubits on your machine. You don't have to wait in queue for IBM for like hours to at least play around with that. So it's already available with Microsoft as well. It's open source. You can use it. You can contribute to it. I mean, I'm also a quantum field ambassador, so I can also get in touch with people who are working into this topic from our side as well. But I guess you do not, for what IBM is providing, you don't have to really wait for the IBM. There are already simulator availables, and of course, it's not the actual quantum computer, but I mean, what the hell? I mean, that's also just an API call to some
Yeah.
computer which is sitting in IBM. You can have that simulator running on your local computer as well, and simulate up to 8 qubits in your, if you have a 16 to 32 GB RAM, a decent size computer, you can simulate those qubit on your physical classical computer as well, with some simulators which are already available in the market. I mean, QDK is of course one of them. From, again, I'm not doing a publicity. There is from Google. There is Circ simulation. There is Casket. There are multiple simulators available right now for students and also for hobbyists to learn around. I mean, I can share links. I can also share links from our side as well. And it's a freeware, open source thing. You use it. If you like it, just contribute to the community as well.
yeah.
Right.
Thank
Thank
you very
you.
much. Thank you very much, Arvind. Thank you.
Right. Thank you for all that information and for the initiative, everyone. Right. I have the next question for Ms. Supriya. Even though the concept of quantum computers has been since the 1980s, I believe Richard Feynman has also stated this, quantum computers way back. So why is it that it is becoming popular, so popular now, and there are also quite a lot of misconceptions about it. So could you shed some light on that? You're muted, man. Actually,
Yeah. So before I share misconceptions about quantum computing, let us go a bit back and understand what is happening in quantum computing, because of which misconceptions are getting created.
Right.
So we have been talking about a lot of quantum algorithms, right? So when we develop such quantum algorithms in real life for solving some challenging problem, it becomes very difficult, in the sense it requires it involves a lot of qubits to solve such kind of algorithms. And with such huge number of qubit, it is practically, like currently, it's not possible to use for getting our desired result.
Right.
This is because with lots of qubits, they tend to have lots of noise in the system, and which can end up giving a wrong result or some kind of biased results. If there are only a few qubits, say 2 qubit, 3 or 5, it is easy to control the noises. But with large qubit example, like 50 or 100 or something, it becomes very difficult to control the environment. There is a lot of research which is going on for reducing such kind of noises with the increased number of qubits. And this is an era where we are able to achieve it, and we call it as NISQ era, noisy intermediate scale quantum, basically scaling the number of qubits. So even though we are in this quantum, our quantum computers are not completely fault tolerant with the increase in number of qubits. Incapable of carrying out any practical task on a large scale. So to get rid of this this problem of being non-fault tolerant, there is something known as quantum error correction. So basically, this is again an algorithm which protects quantum information from the noise. So in order to achieve this error correction, again, this algorithm involves thousands of qubits and processing operation. So it is like we are trying to solve the problem which are rising due to large number of qubits with another set of large number of qubits. So in this, what researchers are doing, they're trying to achieve the quantum error correction with less number of qubits. Meanwhile, there are some other research which are happening, which are basically using innovative qubits to tackle such kind of noise problem. There are like superconducting qubits, there are topological qubits, there are trapped ion qubits. So the research is going on and on with the qubits. So the misconception here is like, mm, still quantum is in research phase, so why we are investing it, why industry is investing, why government is investing in quantum when it is a very nascent stage? True, because in coming couple of years, the research which is happening at a very fast pace, it starts showing its true colors. And also at the same side, industries are investing because they know in couple of years the market will be ready, and they have to be ready in capturing the market at that time. So researchers are investing, industries are investing, government are investing, and in very short duration, like short period of like, or say let's in few years, it will be a boom in the market. So that is the misconception with quantum, which is there in the market, and it is not
Right.
actually true.
Okay. I didn't know about the different types of qubits are there. I did know about that. They use different like electrons and as well as
Yes.
photons. It's for the communication, but a different type of qubit is new information for me. So thank you for that.
I mean, I guess I let me add on this part. I mean, I guess the error correction part is kind of correct, but I guess it also depends on the way you're building the computer as well. So if you think from the
Yes.
from the way the hardware is implemented, there are NISC. I don't like the word NISC. It's a scientific word because they say it's very noisy. So let's call them something so that it doesn't. We are not saying it's all total trash. It's NISC.
Okay.
Let's call it like that. So so it's noisy intermediate. So essentially what they're trying to do with this superconducting NISC style like quantum computer is, we are as of now, we also learned multiple types. Rajesh also mentioned about physical qubit and the logical qubit. So essentially what the idea here is, you have
Right. Right.
you have one physical qubit which is actually, let's call it an electron, just for or an atom of any kind, photon, electron. There are different ways of creating the one. And then so essentially the idea is, we bundle a bunch of physical qubits and put them all same information and then create a big logical qubit, with the hope that majority of the qubits will still retain the initial state in which we put it in. And the error, so the idea here is that let's do a consensus algorithm and then put same information on 20 places, and then hope that all the information will not be corrupted, and hence if we do a consensus, we will do a voting, give me the value, then we'll still have it. So this is why there is the number of logical qubits are way less than the number of physical qubit, because we are trying to basically replicate the information. And then we are hoping, it's just a hope, that not majority of them will have a wrong state, because the longevity of the qubit, the information stored in a qubit for a duration, is right now in microseconds, not even in milli. So essentially it's just gone. You just put it in and it's gone. So this is
Right.
where they are. And but then there are also like other type of like methods by which we are working on, which is like also Supriya mentioned about topological qubit, and this is also what Microsoft is pursuing as well. So we are trying
Right.
to build a computer on a topological qubit. So the idea here is, instead of focusing on each atom and the information stored on each atom individually, we create a topological qubit which will not look at each atom but on a macro atom level. So let's put like a bunch of electron together and then create a macro system, and then put a input. Let's braid the electron like the way we braid our hairs, and the information is flowing, and then what we
Right.
observe is what we pushed into this topological qubit, which is this braided number of electron, and what is coming out of it, which is a different way of creating the computer, not going on each atom level and tell me and asking, measuring that thing, but all looking at more on a macro level. And if we do that, then the hope is that the error in the system will be reduced, because now we are looking at a macro kind of the braided system, not individual atom, which is highly unstable right now. But again, who will win the race? Only time will tell. So it's all in the research
Right.
area.
Right. So, thank you for that addition, Mr. Arpit. So I also have the next question for you. That what does quantum computing hold for the future, and what is the scope of improvement? I realize it has been answered, right? But still, I would like to get your perspective.
I mean, opportunities are tremendous. I mean that's why people are investing so much money into this topic and time as well. So I mean, the thing is, as I already mentioned, there are some kind of problem which are intractable for the classical computing right now. Just think of, for example, material sciences or life sciences. We do not have the kind of capacity with the like the world's fastest computer to even for example simulate a molecule of caffeine. I love coffee and coffee has caffeine, and I just heard like only a couple of months back that now a caffeine molecule can be simulated on a world's fastest classical computer, which is basically a data center of its own.
Right.
Uh, with quantum computer, we can, because it's quantum in nature, we can simulate materials out of the box on these things, or like, but with much ease. And hence, once these computers are available in the market, we will see a huge emergence in the area of material sciences and life sciences, because there are problems about drug discovery, for example, wherein the big pharmaceutical companies have HPCs running this large problem and trying to simulate molecules and look how a drug is basically interacting with that molecule so that we can produce new medicines. This area will be revolutionized with quantum computers, if nothing
Right.
else. This is for me is like really why I would put all my money on the topic, if somebody asks me. Then we are talking about like complex optimization problem. The problem was there since 50 years. We still don't have answer. Traveling salesman problem, graph coloring problem, graph division problem, job shop scheduling problem. These are all classical mathematical intractable problems. I will not say that all of this problem will be solved, but we can optimize it better than what we can do right now. And of course, like AI is everywhere, and we are using AI. So, and also in blockchain, we are using a lot of stuff in terms of optimization. I think that also it will be far-fetched, but I think also the quantum QML, the quantum machine learning, will also be something which will improve the deep neural net, especially the way we are doing reinforcement learning and advanced. So I'm not talking about like really doing basic stuff. So I asked myself, you don't have to shoot the bird with a cannon. Don't do that. I mean, there are problems which are very well can be done by classical computing, and let's keep doing it with that one, and try to solve problems which are really we
Tough, and
cannot do
you
right
really
now,
pointed out.
and use quantum computer to solve those, because otherwise what we are doing is we are shooting a bird with a cannon. It doesn't help anybody. So
Okay, it's not really effective. Yeah.
yeah.
Right. Thank you for that. Humorous comparison. I believe it will be embedded in our minds forever. So, next question for Mr. Rajesh. That how common will their usage be in the future? Like, I believe it's not going to be totally replaced so that it will not totally replace our conventional computers. But what is the level that they will be there?
Yeah, absolutely. Here I will be playing a role of what do you call a person who is seeing through the crystal ball. The relation of quantum computers is very simple. Quantum computers nature. Look at the nature today. You have so much of energy that gets created in through hurricanes. So much of energy that gets created through lightning. So much of energy gets created through the natural disasters. This is all about
Right.
nanoscience and nanotechnology. So for first
Right.
time, humanity as a race is trying to leverage those natural aspects and then apply it to the real world scenario, right? So
Right.
I'm of the opinion that the next discovery or the next giant leap in human race will be facilitated through quantum computers. How?
Right.
I don't know. But will it happen? Yes, I have a strong gut feel that it is going to happen because nature has demonstrated that. And you're basically harnessing the power of that particular nature, and then you're putting that into a computer. So if you're talking about extraterrestrial travel, probably that would be facilitated by quantum computers and not by classical computers. And as Arpit has mentioned, each one has its own role. We are not talking about replacing classical computers with quantum computers, right? And it's
Right.
a natural discovery that happens when IBM or Microsoft or the others started investing in computers. They didn't realize the magic that the computers would do today, right? If you go and see Bill Gates' explanations in way back in 1970s, he said that whatever he had imagined, and he said he will be really thrilled even if a fraction of it would have been accomplished through the classical computers. We ended up accomplishing not just a fraction, but a gigantic portion of that particular fraction. And same is the case with this quantum computers, and where they're going to bring in from a business perspective. Yes, we have a lot of challenges. How can we build a hub and spoke model for an airplane, like traveling that molecular science to be done, drug discovery, a lot of it. This is only contributing to an incremental improvements in human race. And the beauty of quantum is not just incremental improvements, but an exponential improvements, probably the kind of tech that we saw as kids in the Star Trek series.
Yes.
That tech may be possible through quantum computers, right? So at this point of time, it is a wish and it is an aspiration and a belief that that wish and aspiration will come through with quantum computers. Beyond that, I won't be able to demystify. If I demystified, I wouldn't be wasting my time on this webinar. I would convert that into money in the real world, right?
Right.
I mean, just to add, because I mean, I guess I 100% agree with Rajesh what he mentioned about what other and I agree that what the kind of use case I talked about is still very near term. I mean, if you really wanted to be futuristic about what you say, I can already give you one technology which I know for the fact people are working in the research area in quantum is teleportation. If it will ever happen, it will only happen when the quantum computers are there and now they're mature enough. We cannot
Right.
do teleportation with quantum computing because the concept of entanglement
Hmm.
or quantum entanglement is studied in quantum computers, and once they are good enough, once we can achieve the entanglement to the highest order, that we are going in the nano level on a cell level, that we can entangle the atoms efficiently, this would be the foundational block on which we can think about teleportation or quantum teleportation. So if you really want to be Star Trekky, that is, I would say, is something which will not possible. If we fail in quantum computing, we will never be having teleportation ever.
Right.
Let's put it like that.
So in the future, if we have hyperspace, I believe we won't need cars, but still, like that's a long time ahead. Right. So next question for Dr. Suja. That I know that we have heard a lot about China and Google, US side doing much in these fields, quantum computers. Like China coming out with the news that they have the Google of research about quantum computers in India, specifically in India.
Okay. Uh, you see, as far as my awareness is concerned, my awareness is restricted towards the academic side only.
Right.
So, what academic institutions are doing that way highlight. So, Bangalore is having excellence in quantum computing, and there is Raman Research Institute. They are also working in this particular area, and there is also a government side who is and all. So at the moment, I think in India it is in nascent stage. Crore rupees for this particular quantum computing for the next 5 years.
Right.
And the Department of Science and Technology, as well as some other funding agencies, they are also giving a lot of funds to different universities and IITs for the purpose of working in this particular area. So as far as I know, in ISC Bangalore, they have one 8-bit 8 qubit processor that they have developed, and they are working on more sophisticated processors in this particular. Yeah.
Right. Thank you. So the session is about to end. I have my last question for Ms. Supriya. But let's take a look at the student side, right? We have talked about the future. We have talked about what is going on with quantum computers. Let's talk about students. That how can a student with no practical knowledge or no information in the quantum spectrum start this? Can learn about this or even
Yeah.
interested in this?
I think we have briefly touched upon this topic. We have discussed about IBM Quantum and QDK. So
Right.
I can talk more about IBM Quantum experience because I've used it quite some time. So it's actually a wonderful source of knowledge to begin with for a student. It covers all the aspect of quantum computing. That is from the very basic definition of what is quantum to actually running the code on a real quantum computer. So in quantum IBM Quantum Lab, there are two type of quantum computers. One is used for simulation and another is a real one, so you need to pay for the real one, but you can always use the simulator quantum computer. It is free. And there are few things in this IPM quantum experience which the students can explore are like, there are tons of documents and tutorials which are available. They teach you from the scratch. There are various algorithms available there with the code which you can experiment with.
Right.
Available for building circuit using qubits and gates. You can edit it, run it, you can view the result, understand how changing in circuit is affecting the result. There are some more tools available which you can use in for adding noise in the system. For example, the extent of noise, the source of noise, and likewise. So this is basically to understand the real world scenario using simulations.
Right.
There are some valuable extensions as well which one can design, and it can be used by say startup researchers or even independent developers. So IBM quantum experience is like one whole package which covers everything. So I guess students can explore this to understand more about quantum.
Right. Okay, so thank you all for this very interactive and I hope it will be embedded in my mind forever. I would say it was a quite interesting and informative panel discussion. But I am very grateful to all for attending this session and hope to see you again in some future session.
Thank
Yeah,
you.
thanks a lot.
Thanks for having
All
us.
the
Bye bye.
best.
Yeah,
And
thank you very much, Arpit, and thank you very much, Supriya ma'am, for sparing the time for us. Thank you very much.
yeah, thanks a lot, sir, for inviting. Yeah, bye.
Bye bye.
Thank you. Bye bye.